Let us see. So we had started friction last time, but then I ran out of time. So we will finish talking about friction, and then we will get into Newton's third law, and I will hopefully be able to do a problem or two. And then we'll do more Newton's third law, and then wrap up Newton's laws entirely the next lecture. To start, though, let me take a question from a previous exam and say, ponder this. A deli displays sausages in the window. Which of the setups below is the safest? I guess which setup or setups, given my answers. Oh, that's a picture, not text, so that won't work. So never mind. Which of these setups is the safest, meaning that the tension in the rope is the lowest? If the tension is too high, the rope might snap. So instance one, where there's one sausage hanging off one rope, or a rope that's attached to the wall, rather. Instance two, where there are two sausages hanging off one rope, and they're both on the same side. Then instance three, where there are two sausages hanging off one rope, but they are on opposite sides of each other. All right, so let's just solve for all of these, see what the tension is going to be, and see what we get. Let me assume, also in this case, all sausages have the same mass. Each one has a mass m. All right, for case one, there's a sausage. I look at what the sausage is in contact with. There's some tension force acting on the sausage, and then the only other thing is gravity. In that case, I won't bother going through all the steps. This is vertical, gravity is pulling down, tension is pulling up. If the sausage remains stationary, its velocity is not changing, it must be the case that mg equals t in that case. This is a problem where it's simple enough where I would expect that you could be able to just kind of write down the answer from just experience of doing these sorts of problems. Scenario 2, I'm analyzing the motion of the sausage pair. Again, it's in contact with the, we'll call that tension 1, we'll call this tension 2. It's in contact with the rope, so there's some tension force, and of course there's gravity pulling down. The weight of two sausages is 2 times mg, and the tension pulls up. In this case, the tension is 2 mg. So if anything, case 1 is safer than case 2. The rope would be less likely to break with case 1 versus case 2, though I'm displaying half the product. So now let's look at what's going on in case 3. Let me pick one of the sausages. In that case, it's in contact with the rope, so I'll call that as some tension T3. And then there's also gravity pulling down. Looks very similar to what we had before. Here I will actually write it out. In that case, the free body diagram is that gravity points down for a single sausage and the tension points up. So if I define up as positive, I might say that T3 is just plus T, whatever that is, and Fg is minus mg. The sum of the forces must equal 0 because the velocity is not changing. The sausage is just sitting there. Notice here you get that the tension is mg in this case. If we were to go back and do the same analysis for this sausage, we would arrive, if you stare at it long enough and convince yourself, it would be the exact same work. You would arrive at the right answer, or the same answer. That the tension in that case is just mg, not 2mg. I think it's holding two sausages. Shouldn't both of them be contributing to the tension in the rope? How taut the rope is? If that's if there are two anvils on both, one on each side, isn't that going to make the rope strain? And it's not obvious at first, right? if you thought the second and the third case should both be riskier and have more tension in that rope compared to the first case, I would say you're not alone. I think before I stopped to think about it, I would have said the same thing. But again, what's going on is, again, forces occur through points of contact. So if you look at what is going on at an individual sausage, then the rope only has to provide enough force to hold up a single sausage. And since the rope has a uniform tension throughout, that tension is uniformly distributed throughout the entire rope. And so on the other side of the rope, a similar force is being applied to the other sausage. But since that is also enough of a force, a tension force in that case, to hold up the gravity of another single sausage on the other side, the rope prevails, only having a tension of mg rather than 2 mg. And again, if the rope's tension was not uniform throughout, which remember is only the case for kind of idealized thin ropes, this would not be the case. All right, so friction. We were talking about this a little bit before, that we have a model for friction. Everything we're talking about here is a model for how you deal with friction between two surfaces in contact. The example could be you have a box, and you are pushing on the box with some force. That push, F, not sure why it was red, that push, F, if that surface is rough, then friction is going to want to oppose the box from moving at all. So there might be some, we would call it a static friction force, if the box remains stationary. If box stays stationary. If the box is unable to remain stationary, if box moves instead, then you don't use F sub S, you then use the kinetic friction force, F sub K. Friction that is occurring during some sort of kinetic motion, where static friction is dealing with objects that are not moving, and the friction is trying to keep it that way. Kinetic friction is trying to bring things to a static state, to rest. So the direction, if you're ever wondering about what the directions of these forces should be, they always point in the way that opposes motion. So in the case of static friction, if I were to, hold my finger up so that I don't see the static friction force, so there's only one force pointing to the right, I would say that box is going to accelerate to the right. And then I have to think, okay, then what does that mean in terms of the direction that static friction points? It wants to oppose that, so it's going to point to the left. And then once the box, if it's the case where the box actually is moving, the box is moving to the right, kinetic friction opposes that motion, it will point in the opposite direction. And the model we have for this is that the static friction force, or rather, I guess we're talking about the magnitude of the static friction force, is less than or equal to some number times the normal component, where this is just a number, and this is the contact force with the surface. That points normal to the surface, so we call it the normal force. Which we've talked about, does not have to be straight up, does not be diagonal, does not always equal your weight, yada yada. But for friction, essentially whenever you're dealing with friction, you have to ask yourself first, does it move? So you have to figure out, you're solving your problem. If you have a problem where there's a friction force and you are being asked, does the box slide? You have to first assume that it doesn't. Use the static and calculate what the static friction force is, what force is required to keep the box from moving. If that friction force is less than or equal to this maximum value that I've written down here, I'll even give a highlight. If it's less than that value, then you're good. Then, indeed, the box does not move. If the friction that you need to keep the box stationary exceeds this value that I've highlighted in green, then the box does move, but there's still a friction force, but it is the kinetic friction, which is the same thing but with a different number. Essentially, static friction, and actually I have some examples of kind of what these values are. Static friction, you have an object that is stationary. I guess I used this last time, right? I have a box that is I have something that is on this box that is stationary. It is slanted at some angle. In that case, the slant, gravity is trying to make the object go down the ramp. Friction, therefore, is opposing it by pushing up the ramp. And the amount of friction that is necessary in this case is less than whatever the maximum allowed value is from static friction. It remains static in that case. But eventually it gets high enough that gravity wins against the static friction force. The object begins to slide. There's still friction, but it is some lower amount of friction that is dealing with the fact that there's kinetic motion going on. So you can see, for example, the top two are, perhaps very relevant for, your usual safety, or perhaps shoes on wood or shoes on ice. The static friction coefficient is always higher than the kinetic friction coefficient. Physically, why is that the case? You might think of an object as stationary. We talked about last time about really what friction is a very microscopic phenomenon where there's intermolecular forces and perhaps electromagnetic forces that are occurring between the molecules that make up the object and the surface. And I said that sometimes even they can create bonds with one another, so they actually fuse together in very small microscopic locations. And if something is stationary or static, there's more of a chance that can occur and is stable in a sense, where it can create stable, consistent bonds between the surface and the object. Versus if it's kinetic friction, the surface is moving, perhaps quite rapidly across, the object is moving across the surface. There's less time for these strong bonds to form. So the friction, while still non-zero, is not nearly as high as when things were static. And you can see, given that model and given the ideas of kind of what we have from our intuition of friction, dry concrete is safer than wet concrete. The amount of friction is less. The coefficients get lower. Shoes on wood compared to shoes on ice. Walking across, a wood floor is much safer compared to your rubber shoes walking across ice, which the static friction coefficient is quite low. Which is why, you have to be very careful when you walk across ice. It's very easy to slide. Or, for example, why sledding works. Steel on ice and steel on snow is somewhat similar. Steel creates a very low amount of friction between it and ice or snow. So then, let's solve a problem or two. Here's one from an old exam we could start with. A box with a weight of 40 newtons rests on a rough surface. A 12 newton horizontal force is applied to the box. If the coefficient of static friction is 1/2 and the coefficient of kinetic friction is 0.4, the magnitude of the friction force on the crate is what? So hopefully you have paused and have gotten a chance to try it. And it's rough, so now that we are dealing with rough surfaces, whenever things are rough, I will kind of shade in the surface to imply that there is potentially friction. All right, so my force diagram, there is a push, there is gravity, and then there is now a contact force that both is there's a perpendicular component, or the normal force, and then there's also a parallel component, which is friction. So I would say there's some sort of surface force, which can be both the normal force plus friction. I will treat them as two separate forces, but really they're both kind of one and the same. All right, so the free body diagram, there's gravity that's pointing down, the weight, which is just mg, but I tell you that the weight is 40 newtons. So let's see, so if up and to the right is positive, this might then be negative 40 newtons. Downward. I'll use the IJK notation. I haven't done that in a while. There is a contact force from the surface, so the F floor, or the normal force if you want to call it that, which has some value n, and it's also in the vertical direction, and it is positive. I did not write these well. So I now have no more room, so let me move these over. Zoom out. There's the force, there's a push. There's a push that's being exerted on the object, which was 12 newtons in the horizontal direction. So I'll use I for that, plus 12 newtons. And the question is that there's then some sort of friction force, F, which I'll just write now as script F. And this problem is asking you to decide, actually, whether it's static friction or kinetic friction. And depending on your answer there, what then is the magnitude of the force? So for friction, the first question to ask is, does it move? So with friction, you could first ask, does the object move at all? Is the object moving, or is friction able to keep everything stationary? So the way I usually approach these problems is I assume it does not move and calculate what friction I need for that to be true. So in that case, if I were to do that, the sum of the forces on the box equals the mass of the box times the acceleration of the box, but I'm assuming the object is not moving. Therefore, in the x direction and in the y direction, I can write down how the forces balance one another. In the y direction, you should see that it's n minus 40 newtons, or that the normal force equals 40 newtons, or the weight. In the x direction, it looks like I'm saying there's the force from the push minus friction, since friction is pointing to the left, equals 0. So that implies the friction that is required to keep things stationary, in this case, is 12 newtons. So now the question is that possible? If things are not moving, if no movement, then this force we just calculated must be less than or equal to the maximum possible answer for static friction. It can be anything up to and equal to that max value, else static friction is not enough. So the left-hand side is, so the question then is 12 newtons less than or equal to the coefficient of static friction times the normal force? Coefficient of static friction was 1/2. we calculated the normal force was, I'm writing down the answer, was 40 newtons. So this is 20 newtons. In this case, 12 newtons is less than 20 newtons. True. So in this case, I would say, so box does not move. And the friction that is being experienced is minus 12 newtons in the horizontal direction based on this coordinate system. Now, you could ask, what if, suppose this inequality where I wrote true, perhaps that was not true. Perhaps you got something like 12 newtons less than 8 newtons. That would obviously be false. So what you would then do is go back, start the problem over, but then you cannot say the acceleration is 0. You would have to say the acceleration is some non-zero value. And friction there then is not unknown. You know in that case, if there's motion, what friction is. Therefore, then it's the kinetic friction, mu k times n. So there's a number, where here was what we had to solve for. And then you would be able to solve for the resulting acceleration on the box. For example, suppose we have a box which is 5 kilograms in mass. My angle is, of course, 30. This is 2 meters. I don't think that's needed. And the question is, if the static friction coefficient is 0.6 and the kinetic coefficient is 0.3, does the box move? And if so, with what acceleration? All right, we're off and running. So my first step would be to assume no movement. Therefore, I know the friction force is static friction, and we just need to make sure that it is not too great. There's only a maximum amount of static friction that is possible. All right, so my system, the box. What is touching the box? The surface is touching the box. Both, and there's friction as well, so there's both normal and or there's a surface and friction results from the surface. And then there is gravity. So let's say gravity points downward. And I'll again have up and to the right as positive. So F gravity, I might say, is negative mg in the y direction. It is in contact with the surface of the ramp, which maybe I'll draw it as this. The surface is this. It's not a force. That's why I made it a different color. But the surface, there's a surface force, which is F surface, which has some horizontal and some vertical component. Its magnitude we might call N, if you are so inclined. And there is static friction. So we have to think, if there is static friction, what direction would we assume it's pointing in? And we can assume that the friction is pointing kind of up the ramp in this case. The box wants to go down the ramp. Friction is preventing it from doing so, so it is pointing up the ramp. All right, so we will use a coordinate system, parallel and perpendicular to the ramp, like we've done before. In which case, I will define down the ramp as positive and away from the ramp as positive. That should be nothing new. We did that in the previous lecture. So then in this coordinate system, I can write down, what these forces are. So the contact force is very easy. Sorry, I'm using IJK this lecture. The contact force, there's nothing along the ramp, and there's some positive value perpendicular to the ramp. The friction force points parallel to the ramp. What a great coordinate system. So it just points in the negative direction along the ramp and has no component perpendicular to the ramp. I reverted to the notation I prefer, but we're using IJK today. And then in this case, this is the one instance where gravity now has two components. The part along the ramp is mg sine theta I, and then the part that is perpendicular to the ramp is minus mg cosine theta j. Minus because it's pointing down into the ramp. It is pointing more this direction, which is at the negative direction. Alrighty, so then again, F equals ma, or rather the sum of the forces equals the mass of the box times the acceleration of the box. If we are assuming the box is not moving, then we can set the acceleration equals 0, or rather it's remaining stationary. Usually the easier case is the perpendicular to the ramp part, which is, if I wanted to highlight, it's dealing with this, and it's dealing with this. So then that says n minus mg cosine theta equals 0, or that the normal force is mg cosine theta. Did I calculate this in advance? I did not. So now we can then look parallel to the ramp. So if this was green, I might say parallel to the ramp is the I component. So then in this case, I would say mg sine theta minus the friction force equals 0, or that F equals mg sine theta, which mg sine theta, I did pre-calculate, is 24.5 newtons. That is the friction force that is needed to keep everything stationary. So then the question is 24.5 newtons less than or equal to the max value of the coefficient or the friction force when it's static, which is the static coefficient times n, which is the static coefficient times mg cosine theta. Because we figured out what the normal force was in the previous part. So in this case, it is again 25, or not again. We could plug all these numbers in again and get that the answer is 25 and a half. I would say that's true. So in this case, I would say the box does not move. And therefore the acceleration is 0. What if theta was not 30 degrees but 45 degrees instead? We could redo the entire problem saying, okay, I'm going to assume nothing is going to move. The math obviously stays the same, but now we have a different angle. So in this case, this becomes 34. Sorry, that's supposed to be sine, not cosine. So this becomes 34.6 newtons instead. And Fs max, which is the coefficient mg cosine, becomes instead 20.8 newtons. So then F less than or equal to F static max is false. Which all that means is the box actually moves. We now have to go back and redo parts of this problem to calculate what this acceleration is. So then I would say go back, assume a long ramp is not 0 like we did before. And now the friction that you experience is not some unknown that we had to solve for, but it is now the kinetic friction force, now that there is motion, equal to m mu k times n. The vertical component, or rather the component that is perpendicular to the ramp, obviously does not change. The box is not being pushed more or less into the ramp. The normal component does not change at all in this case. So really the only thing that changes is that the sum of the forces now in the parallel to the ramp direction, in this case, becomes mg, actually, rather than me just do that, let me just see what we wrote up here. We could copy it out. Parallel to the ramp, we could cut that. We could paste it here. But then I'm going to put an x through that because that is not completely correct. So that has to adapt and change now. Instead of that, it becomes, let's see, the gravity force stays the same. It's still mg that, but now it's minus fk equals mass times acceleration. Now there's friction. There's still friction, but now it's kinetic friction, and there's an acceleration in this case. So then this becomes mg sine theta minus mu k times n. But what was n? mg cosine theta equals ma. All those silly m's go away. And as a result, the acceleration of the box down the ramp, though with friction in this case, is g sine theta. But now friction slows things down. So there's this term also to consider as well. And if we plug in numbers, I get, for 45 degrees, I get that A is something like 4.85 meters per second squared. So again, it's assuming that nothing is moving. If you can convince yourself that actually something is moving, go back, assume that it's kinetic friction instead, and figure out what the resulting acceleration will be. How are we in time? Is that true? Yeah. doing great on time. Alrighty. Newton's third law. You might have noticed we skipped over this if you're following the book. I did friction first before going back to Newton's third law. Because I think Newton's third law, conceptually, it is the hardest of the three. The first law is perhaps the most non-intuitive, because of friction. Newton's first law again says that everything stays in motion unless at a constant speed, or constant velocity rather, unless forces act upon him, the object. The second law, of course, is F equals ma. The net force equals the mass of the object times the resulting acceleration. Tell me what forces are in contact with the object, plus maybe gravity, and I'll tell you how the object is going to accelerate, how its velocity is going to change. Newton's third law, which is the only one of Newton's three laws that he could not argue directly through proof. He wasn't able to prove what we now call Newton's third law in any way. But he argued this by appealing to experimental results and using that as a justification of something where it's like, I'm not quite sure how to completely prove this, but this is what the evidence suggests, and it really does seem like a profound kind of law of nature. And turned out to be right. I've alluded to this, but we will see Newton's third law is also nothing different than the conservation of regular momentum. So the way it's stated is that two objects in contact with one another exert equal and opposite forces on one another. So what this says is when I am holding up an apple like this, if I were to do a force diagram of the apple, we would say, well, there's gravity pulling down the apple, but the apple is also touching the hand, so the hand must be exerting a force on the apple. That would be correct. I could now then do a force diagram for my hand. And I would say, okay, gravity is pulling down on my hand, but my hand is also in contact with the apple. So the apple must also be exerting a force on my hand. And Newton's third law is saying that there is a connection between some of those forces in between the two systems. One system of the apple, the other system of my hand. Here there was a force from my hand. Here there was a force from the apple. Those forces are actually related to one another via Newton's third law. That they actually have the same exact magnitude, but point in opposite directions. So the cutesy way this is sometimes said, if I punch the wall, it hurts. Why does it hurt? Because the wall has also punched back on me with the same force that I punched the wall with, equal and opposite. So while I might damage the wall as a result, my hand also hurts because the wall exerted the same force back on my hand. This apple is being pulled down by gravity, but is being held up by my hand. My hand is also feeling the weight of the apple down on it because there's a contact force. There's a contact force between the apple and my hand as a result. I feel the presence of the apple holding it up. In this case, it's a very light apple, but you can imagine if I were to do this with an anvil, I would really detect the presence of the anvil on my hand, for example. And these pictures that are also on the screen are kind of examples of Newton's third law in action. Let me shrink it because there's an animation as well. In the case of the swimmer is pushing off the wall in order to propel themselves forward into the water. What's really happening? They are pushing to the left in this picture. Their legs are pushing left against the wall. So as a result, the wall is pushing on the swimmer to the right. The wall is pushing the swimmer to the right. And that force from the wall is what is pushing the swimmer forward into the water. It is the wall that is doing the force, exerting the force, which arises because the swimmer is exerting a force on the wall. similar to the birds flying. Birds are flying because they are flapping their wings down on the air. They are exerting a force on the air beneath their wings, and as a result, the air is exerting a force back on their wings. That force from the air being exerted on the wings pushes upwards on the bird, and what allows the bird to remain in flight. It is the air that is pushing up on the bird that's keeping them in the air. And then similarly, the rocket. The rocket's something that you could experiment if you're ever on an ice rink, for example. Two ice skaters on an ice rink, you've also experienced this as well. You're seeing Newton's laws in action. So how does a rocket work? A rocket is propelled into the air because of that massive amount of force that is being exerted by that jet at the bottom. But where is that force coming from? What really is happening? What's happening is that in the jet, the fuel is being converted to energy, and that fuel is being shot out of the bottom of the jet at incredibly large speeds. It takes force from the rocket. The rocket has to exert a force on the fuel as it shoots the fuel out of the bottom. As a result, Newton's third law, the rocket exerts a force on the fuel as it throws it down towards the ground as exhaust. Newton's third law, that then pushes, the fuel that's being pushed out then exerts a force back on the rocket, pointing upward in that case. And so it is pushing the entire rocket forward into the air. And I say you could experience this on an ice rink. If you have two friends that are on an ice rink and they're holding hands, and then one of them pushes off the other. They don't even necessarily have to both push off one another. Just one of them could stay perfectly still. The other one could push themselves off the other ice skater. Both of the ice skaters move, and they will both move at the same rate. That push that you push on the stationary skater exerts a force on that stationary skater. They will start to move away from you. But if you've ever been on an ice rink, you don't stay still also in that case. You pushed on the ice skater, you also then start moving backwards as a result. Just on an ice rink, if you push off the wall, and then you move backwards. In that case, you push on the wall, exert a force on the wall, but then the wall pushes back on you, which is what then pushes you back into the ice, or onto the ice rink. So equal and opposite forces occur between systems. This is why when we were talking about force diagrams and free body diagrams, I made the comment that systems cannot interact with themselves. If I'm analyzing, and you might think, why is that, why can't systems interact with themselves? And really they can, but because of Newton's third law, nothing would result as a result. Nothing would result, period. For example, if I were the system and I'm analyzing my motion, perhaps I'm standing on an ice rink. So there's no friction, there's nothing else. I'm standing on an ice rink, and I push on myself. Obviously, by me just pushing on myself with my hands, I'm not going to start moving on the ice rink. And if you were to do that analysis as, say, as a free body diagram, so I'm pushing on myself, push. In the system that is me. Essentially, if I were to try to analyze that, what's happening is one of my hands is pushing on me, but then the other hand is pushing in the opposite direction because of Newton's laws. Even maybe I don't even have one hand. Maybe I just push on my face while I'm standing on an ice rink. I'm exerting a force on my face, but I don't start moving in one direction, because I'm exerting a force on my face that might be pushing me to the left, but then my face is exerting a force on my hand that is pushing me to the right, that are equal and opposite. They cancel out. I don't actually move and go anywhere. So when I say that systems can't self-interact with themselves, really what I'm saying is that if they are interacting with themselves, there is no net force as a result. There are two forces involved that will be equal and opposite. And they will essentially just cancel each other out when you do the actual mathematics. So I would say that these cancel each other. We can take this a step further. And I could say this is also telling us that forces come in pairs. Maybe I'll say companion. Each force has a force pair companion. I push up on the apple is pushing down on me. Those two forces are a force pair, which are connected by Newton's third law. I'm sitting on the chair, pushing down on the chair because I'm in contact with the chair. The chair is pushing up on me. Those two forces, me pushing on the chair and the chair pushing up on me, are a contact force pair. They are related by Newton's third law, are equal and opposite in magnitude, or equal in magnitude, opposite in direction. Less obvious examples might be when the apple is in the air, gravity is bringing the apple down towards the earth. But by Newton's third law, there must be a force pair companion for that gravitational tug. Earth pulls the apple down. As a result, the apple is also pulling the earth up. Earth is exerting a force on the apple. The apple is also therefore exerting a force on the earth. Every time you drop a ball down to the ground, you are actually causing the earth to ever so slightly move as a result. It looks like the apple is moving and doing all the motion because Earth is pulling down on the apple with a gravitational force. But by Newton's third law, the apple must therefore also be pulling up on the Earth with the same gravitational force. More on that. So I could say every force has a force pair companion. Force pairs occur between systems. Again, systems don't self-interact. With force pairs, if you're trying to identify force pairs in free body diagrams, force pairs occur between systems. Let us think of an example. Suppose you have your hand and you're holding a box. That's supposed to be a hand. Hand, box. I could ask, what are the forces acting on the box and what are the forces acting on the hand, and try to identify force pairs that result. So now let's first do the box. So for the box, the forces I would identify on the box is, okay, there's a gravitational force pulling down on the box. It is also in contact with the hand, so there is a force from the hand as well, pointing upward. And that's it. I could now look at the hand and do a free body diagram for the hand. Gravity is still operates on the hand too, so there's force of gravity on the hand. But then I'm also in contact with the box. So there might be a force from the box being exerted on my hand as well. And Newton's third law allows us to identify that this force and this force are a force pair. I act on the box acts on me. I punch the wall punches me. That would be an example of a force pair. I could write down that F box, it must therefore be true, is negative F hand. and I'm writing this as vectors, notice, so that's saying that the direction the force points for F box, which I drew down, is opposite, because of the minus sign, the force from the hand, which points up. Do not confuse identifying force pairs within the same system. Notice that there are two systems here, the blue box and the red hand. And the force pair occurred between two different systems. Objects don't self-interact. You might say, fine. But you said every force has a force pair companion. What about these two gravitational forces? Okay. But in that case, we need to realize that there's a third object here that we are ignoring, and that is the Earth. So this is all happening on Earth, where Earth is exerting a gravitational pull. Should have done that in black. I don't know why I did it in green. Which then I can identify my third system, which is the Earth. And I can say, what forces are acting on the Earth? Now remember, by Newton's third law, we're saying that forces come in pairs, and if the apple is being pulled down by the Earth must therefore be being pulled up by the apple. So since Earth is acting on the apple also acts on the Earth. So I'd say this might be force, gravity, apple. Oh, sorry, it's a box for this problem. And then there's also a force related to the hand as well. And I'll put little primes here for, that's what's being felt by the Earth compared to what's being felt by the box in the hand. But there's a relationship. By Newton's third law, these two forces are equal and opposite. I could say the F of gravity on the Earth by the box is minus the force of gravity on the box. If you say the force of gravity on the box is the mass of the box times little g, then the Earth is also feeling a force of little m, the mass of the box times g, but pointing in the opposite direction. And then similarly, I looped around the wrong side. Those two forces are also a force pair. I can say that F of gravity on the Earth from the hand is minus the force of gravity on the hand. If the mass of my hand times little g is what my hand is feeling, the Earth is feeling the mass of my hand times little g on the entire Earth, but pointing in the opposite direction. And therefore, notice, we've identified everything and have found a pair for every single possible force. And that is always the case. All forces come in pairs by Newton's third law. Every force you draw has an equal and opposite force on some other system. In the case of the box and the hand, it was that the box acts on the hand acts on the box. With long-range forces, the gravitational tug on the box is the same as the gravitational tug of the box on the Earth. So that's another comment to make. Similar types of forces make force pairs. For example, if you have a long-range gravitational force acting on, say, this apple, the force pair, the other force of the pair, is also a long-range gravitational force. In this case, acting on the Earth. I'm in contact with an apple as I hold it with my hand. There's a contact force between me and the apple. So therefore, by the Newton third law pair, then is another contact force between the apple and my hand. So again, since gravity is the only long-range force we're thinking about today, or for this semester, just remember that gravitational forces form force pairs. You will never have the case where it's, say, the gravitational force on the apple is equal and opposite to the contact force from my hand. That would be incorrect. Let's see, is there anything else I wanted to say about that? Identify all systems. There's also a handout version of this in Moodle that I used last year and will likely appear in what we do in class as well. All right, let me do a couple more examples of identifying force pairs, and then that might be it in terms of what we do. All right, so suppose I have I am holding, I put a little tail on this guy. So here's Geo, my cat, here's me. I am holding Geo, Lion King style, into the air. Let us just identify all the force pairs in this setup. So what is every single force pair in this? So the first thing to do is to identify all the systems. So I know that Geo the cat is going to be a system. I am going to be a system. And when identifying force pairs, usually that also means that the Earth itself has to play a part. Because either you're in contact with the Earth, like I'm standing on the Earth, or gravity is pulling down on me and Geo. All right, so let's do, I guess I could do Geo first. So Geo has some mass, so there's some gravitational force on Geo. I am also touching Geo as I hold him up. So there might be some, and if I'm holding him up, maybe I'm holding him up vertically. Maybe there's some force from my hands on Geo. And I think that's it. There might then be me. I have some mass, so there's the gravitational force on me. I am also touching the ground, so there's a force, so I'll just call it F ground. And then I'm also touching Geo, and kind of anticipating what the answer is going to be, I might write it like this. So this might be Geo on hand. Because Geo is touching the hand, there's a contact force between Geo and the hand. Then there's the Earth. I am touching the Earth. There's a contact force between me and the Earth, so I would imagine there's going to be some force, which is F, I guess, Aaron on ground. Nothing to do with gravity, just the fact I'm touching the ground. But speaking of gravity, the Earth is pulling down on Geo, and the Earth is pulling down on me. So I expect that there will be other gravitational tugs. You know, Geo is also pulling on the Earth. I am also pulling on the Earth. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's an even number. That is promising. So now we can try to identify which of these are force pairs. Maybe I'll try to do this with a highlighter. The hand ones are, that's an easy one at least. You know, I'm touching Geo with my hands, Geo is touching my hands, so therefore those two forces must be related. I'm touching the ground, so this ground force, you know, the ground pushes up on me, I'm pushing down on the ground. Let's see. Gravity is pulling down on me, so therefore I'm pulling up on the Earth. And last but not least, gravity is pulling down on Geo. Geo is pulling up on the Earth. Those are all the identified force pairs in this problem. So, for example, I could write, the force of hands on Geo must be equal and opposite to the force of Geo on my hands. Whatever normal force I write down for me on, in contact with the ground is equal and opposite to whatever contact force the Earth experiences as I push down on the ground. And tomorrow when we do, or in the next lecture when I do some problems, these relationships will be helpful because I can then start to look at things like, I have a box which is attached to a rope that I'm pulling, say. So I am pulling with some force. And if it was just one box, that's pretty straightforward, but what if then that box is attached to another box, which is attached to another box? And I want to identify what is going on, what is the overall acceleration maybe in this case, and then there might be different tensions in the strings. Which of these strings is most willing to break? If they're identical strings, which one has the most tension and might be most at risk of snapping, for example? Or in the case of there's a table, maybe there's, you have a stack of books, and then you also have your laptop, on top of those books. You could ask, what are the forces that each book is feeling? There's, the table itself is kind of balancing all three objects, but this book at the bottom also has to hold up the laptop and one book, where the second book only has to hold up the laptop. So what are those mutual forces that are going on in between all those objects? And what this will come down to is it will again just be a bunch of F equal ma problems that you have to write down. But now you have different systems you can look at, and you can make connections between the systems using Newton's third law as the kind of thread that allows you to go from system to system. Again, by the idea that all forces come in pairs.